Very good morning, Salam Sejahtera and Selamat Ramadan. And also to those fellow Muslim friends and who are fasting, Selamat Berpuasa. Thanks very much. And during this holy month that we managed to carry on a second part or special event we offer for University Malaya this quarter. And I saw some familiar names once again, those who've been coming regularly to our previous sessions about such as data analytics, optimizations on networkings and graph, artificial intelligence, machine learning. And for this particular, the second part this quarter, we are very happy to share with you about optimizations. Of course, if you're in talk about optimizations, there are many ways and different forms, algorithms for different application. And for this particular session, about 1.5 hours, we'll quickly share with you how the automated approach by Wolfram, or better known as Mathematica or programming, that actually will make your optimization in linear or non-linear equations become very simple. Of course, when it comes to optimization, linear and non-linear equations, people generally use it in engineering, such as signal processing, signal analysis, finance, statistics. Those are very common. And for linear equation or linear programming, people use it very frequently for optimization in operation and business. But something like what I have observed in the past many years, about 2 decades, I've been working in these industries, and I noticed that a lot of things that we have shared about in a classroom about optimizations, it actually is very much less utilized in business world and operations. So this is something like quite actually, in a way, I find there's a big gap, especially in academic, especially esteemed R&D, the academic institutions like University Malaya. And we hope that together with this Wolfram technology language, with a lot of automated approach, we can make those actually the gap become narrower, especially those who are professional like you in academic world, you have a strong theoretical background. And Wolfram actually approach it more like not just a strong, solid foundation for mathematicians and engineers. You also, in the past, at least I've seen myself in past 15 years, Wolfram make the entire coding or programming environment more toward like codeless or script-based kind of solution approach manner. So you still can go on a fundamental one with a lot of theoretical research and R&D using Wolfram language Mathematica, or you can make use of language, make use of theoretical aspect you already have, transform into a solution and can help business work. Now, let me share with you what does mean automated approach that can bring the gap between the business world and academic world actually becomes narrower. So by showing you some of the quick examples and some of the current workflow on optimizations on linear and non-linear equations in Wolfram Mathematica. Now, if you talk about optimization model, if you look at linear equations, of course, on the left-hand side here is fairly simple. Now, if you look at here, traditionally we have linear programming, and of course, we look at something like slightly more complex. We have the simplex method or convex linear optimizations method. There are several other methods available that actually quite a huge number of libraries that built in to handle linear programming. I'll show, actually, I'll not show those traditional linear programming later, but of course, I show something that we real application. Then another one is actually much more applicable to business world, but actually slightly complex in linear programming. And you will see that actually could be easily achieved using Wolfram Mathematica. On the right-hand side here, of course, we have a lot of non-linear. In real worlds, like when it comes to engineering, we have a lot actually non-linear polynomial we have to deal with. How do we actually optimize? Of course, when I look at here, we say, okay, first thing ask yourself, are you dealing with certain global optimum you're looking at? Or, of course, like very frequently in engineering world, we are looking at local. Yeah. Now, if you look at here in the local optimum, looking at that, there are two actually major set of automated functions that you can look at. Very simple. Right hand side here, you see that those actually automated super functions in Wolfram, we call something called find minimum, find maximum. Either one is fine. Yeah, as you know, is we are looking for optimum point. Is depending how we look at that. Either find minimum or find maximum or find fit. Now, if your problem is big enough, usually we use this approach. But more than frequently, we need to use numerical approach that with something called n in front. We actually find n minimized numerically, actually try to derive what is a minimum point, maximum point. So same thing here, n minimized on n maximized. So this is like actually we're looking at slightly fairly smaller problem we're looking at. Usually we try to use n minimized, n maximized. Now, of course, we can use it interchangeably, and depending on what kind of situation you try to deal with. Now, later on, I share with you how this automated approach actually helps so much. Now, again, like I say, we in academic field, we have strong theoretical background, and we are not here to go through what those things in the textbook. But rather I share with you is with a strong theoretical background, how you can quickly get the result you want, and or compare some of the result from Wolfram Mathematica with some of the codes you already generated in Python or R. See, hey, the algorithm come up with, does it come close with a commercial package like that? It automatic package like black box package. Of course, you can further actually dive in, say, hey, how does it do estimation? What kind of method use? What's the number of maximum iteration is used when you search for optimum minimum? There are many other things you can manipulate in a very low level in Wolfram Mathematica. But now, later on, I'm going to share with you in very high level. Now, of course, if you say, hey, can I solve it symbolically? I want to look for exact solutions. Same thing. There are super functions here called minimize, maximize. Now, in short, actually, there are only 4 super functions. Minimize, if solve it, look for these symbolic solutions, or I want to look for numeric solutions, numerically minimize. Or I want to look for something that's slightly bigger, is actually polynomial. I use find minimums or find fit. There are only 4 super functions most of the time. Of course, on top of that, you can say, hey, I want to choose certain methods I want, for instance, interior points or Lagrange approach. Yeah, certain things that you might want to actually specify on your own if you want to. But now I skip on part. Now quickly here we see I put this in this quick table so we can have quick view what it's all about. Now on here, you look for find minimum maximum like I mentioned here. This is a numerically derived local optimizations. For instance, here, the method used could include like nonlinear interior points, as I mentioned. You can use a second, most of the time, of course, you can, those set libraries involve a secondary derivative. And when it comes to numerical approach here, for global optimization, we have n minimize, and we will look for, so there's some the built-in method here. For instance, you have the simulated analytics and random search. Yeah, and if we look at here, the global optimizations symbolically, and we have cylindrical algebraic decompositions, yeah, so and so forth. Later on, I'll show with you where to look for those number of detailed explanations, how the methods are being utilized either manually or automatically later on. So this is quick overview on the very top level. And of course, when it comes to linear optimization, linear programming, we have the like a simplex method, interior points, so and so forth, and many others actually methods allow for our own consumptions. Now, very quickly, again, I know many of you might have used your own package, either it's MATLAB or Python or R. Either way, yeah, you those who are dealing with optimization engineering, quite likely you already figured out some of the methods. You use it either for own calculations or teachings or learning. But I'm here to share with you is those who are familiar with Wolfram Mathematica, you will come to appreciate how simple and neat the whole interface to get a result that you want in a very straightforward, actually, a friendly manner, and to even to a lay persons. The learning curve is very short. This is something that a lot of people like about it. Now, I'll share on only because we only have 1.5 hours. And for this training class, not to worry, everything that I'm sharing now, and Desmond will post it or already posted it in a chat room or in an email that you have received maybe later if you want especially us to send to you. The whole training file, everything there's no hidden secret. Everything what I'm showing here, I given to you. No copyright. You can, if you will say, hey, this is very good for my teachings and learning, you can replace my name here. I don't even put my name there. You can just replace with your name or picture. Say, I'm going to use this one for teachings and learning. You're most welcome. And again, this class will come with a certification. So do make sure you stay until the end of these sessions, until 12 o'clock. And Desmond will give you the link how to get your digital electronic copy or certification. Now, if we look at here, local optimum, we start with nonlinear first. I give you 4 simple examples for nonlinear polynomial. Now, if you look at trigonometric functions, now, first thing we look at trigonometric function, and also we look at nonlinear for global optimum. We have transcendental functions, polynomial function with closed and bounded constraint. Very simple, commonly seen scenario. And also we have one convex function with convex constraint. How do we actually deal with a very simple one to slightly intermediate level of optimization for nonlinear polynomial? Now, first, you look at a very simple thing with the trigonometric functions where x cos x. Now, before we solve this simple, actually trying to look for global local optimum for these nonlinear problems, and we want to visualize it so easy to see. We see the entire thing here, x cos x, is exactly how we see in textbook. Now, of course, if I expand now, I say, hey, I want to do some plotting. How do I plot it? Now, of course, it's syntax. Whole Wolfram language is programmable. It's like Python, but like I say, it's much neater and also very lean. And look at here, I just want to plot x cos x. Well, x, I want to specify a range. I want to see only from range of 0 to 20 because after all, I want to look for a local optimum between x when it's in the range of 0 and 20. So this is how it looks like when we try to plot it. Now, if you look at here, I want to look for local optimum. Quite easily to see here is somewhere here. Yeah. Now, or if I want to look for particularly this local optimums when this is in the range of from here, somewhere here to here, then I will tell the system where should I start the searching point. I should search a searching point between certain forms when x is for certain between certain range of domain. Now, in order to do this, very simple. So the next thing is, if you see what I already say, we just now on the very basic overlook of the chart. Left hand side is the linear optimization, right hand side a nonlinear optimization, and we want to look for some local optimum. So the approach here we want to use here is very simple. We're going to find minimum. This is a numerical approach. Now, for numerical approach, I say, hey, I want to find minimum. Of course, if we say find minimum, I have to tell that, hey, the searching point is from somewhere near x is 7. I want to search it start from x is 7. Well, the range here again, like previously, is 0 to 20. Say I start searching. When I start searching here, the system tell me that, oh, this is the result. Well, x is 9.5299. Here, let me just point to this part of formations. Well, x is here. Yeah, my x is 9.52933. So y is somewhere is minus 9.47729. So it's very straightforward. Yeah, this is geometric function, very simple. Now, if we look at the next thing here, of course, you say, hey, fine, I know it's here. How do we visualize it? Now, visualization deployment, of course, if it seems here most of you are scientists, academics, so to you, it might not actually matter to you that much. But if you come to a class of teachings, when class is share or just public in your certain white papers, or you want to deploy it in some like mobile device, Wolfram Mathematica can easily generate to HTML mode, or you can actually turn it into a cloud-based API, so people actually can easily actually put in whatever parameters they will have in their mind. Then, very importantly, visualize it. So to visualize here, again, now I have these actually hold these solutions. Now, if you're familiar with Python programming, of course, this approach is fairly simple. Like like in the programming communities, is usually syntax we use. For instance, here, if I put my solutions one, if this is actually try to tell us that which part actually information we want to extract. Now, if we want to extract this part information, for instance, the first part, yeah, I put double square bracket. Now you go extract the first part information, which is y value, and second part information, this is x value. So if I extract this value like this, I say, hey, this is x with the arrow pointing to the output value. Now, those who are not unfamiliar with programming, you know, hey, this arrow, it looks like something like column symbol you use in JSON. Yeah, if you are dealing with data a lot in exchange the data in a data server, people use JSON format a lot because it's like dictionary. So I say, hey, when this is a dictionary, that means it has something to do with key and value. So in this case, I'm only interested in the information about value. So I say, hey, just give me information of value. I do give me the key. So I just type in value. So then it will give me the x value. So in this case, I can easily extract xy coordinate. So if I extract xy coordinate, I say, hey, I put it together, this xy coordinate, I append it so it becomes xy coordinate, become my points. I say, show my block. I show my block on two things. One is my previous block called my block, and now also with my block size 0.04 be a blue color, and the point is on this xy coordinate, and the system will nicely actually superimpose as many graphics as you want in one display. So in Wolfram language, one of very commonly used actually syntax is called show. You can show and superimpose multiple different graphics as long as they share the same space and time. That means our same layman terms share the same way of coordinations. Then you can actually superimpose multiple graphics like this very nicely. Then you can actually able to deploy it, to share the result or print the result, or actually to transfer the result to be something that user manipulate, user to able to manipulate it. Now, the next thing here, if I look for actually like nonlinear, now this is a quite simple approach. We have these trigonometric functions, sine xy. Now, similarly, if we want to deal with sine xy, I say, hey, how does it look like? Again, sine xy, of course, is 3D dimensions. I go and plot 3D. So I say, again, I want to define the range. It's for minus 2 to 2, y is from minus 2 to 2. Well, give me the 3D display or size xy, how it looks like. Now, this is like what we will expect. This is like 3D display or sine xy. Now, again, in this case, of course, we can get a global optimum. And again, if you want to get a local optimum, we have to tell the system where to look. Yeah, where to look, where to start looking, where to start searching. So are we searching from particular part of this part of the region of the block? This one is like optimal, or we are looking at somewhere here. Yeah, you have to tell the system where to look. Again, this is like we going to how we solve this hang on, then let me just switch my zoom a little bit. Yeah, this thing will go away. Just, yeah, here we go. Now, how do we solve these trigonometals and the trigonometals are actually local optimum? Now, in this case here, I want to search for nearest local optimum. I will need to define, for instance, I want the nearby to be x equals 0, y equals 0. So very simple here. Again, using the exact same functions, find minimum. Yeah, find minimum. Same thing here. I define find minimum where will be this sine xy. And again here, I want to start from x0 and y0. And again here, give me the solutions. The solution is say, hey, if you actually want to find the local optimum near the x is 0, y is 0, say, okay, the value is -1, z is -1. Well, x is 1.4938, y is -1.0514. And again, if I want to display visually easy for us to see, we can use that same approach. You see, in one of the things we like a lot about Wolfram language, a lot of people like a lot, is the standardizations. When you approach things, you can easily construct your own workflow. Every time we're dealing with a similar nature's problem, we see the way we stack up our workflow is the same. You only have to change some little bit, some of the input and output and parameters, a little bit equation here and there. The rest actually step is the same. So now I want to display it. Where's my point? Right? Where's my XYZ? Now it's of course a 3D dimension XYZ. But I say, hey, give me X, this value here, X, here, XY, and this is Z. Now show me the informations. Now you give me the information like this. Now the exact local optimum here we see here is insert beneath here with little cylindrical here. Then we see the little sphere on top. Of course, the sphere here, I can make it a bigger or smaller. If I put a 0.3, make it even bigger spheres, that it looks like. Yeah. Now, see, this is very powerful. Then, of course, it looks like half sphere because like in this particular plane, it cuts through this little sphere. So we look like it's a cup or ping pong ball being slide through in the middle. Now, interestingly, now we look at here, if we want to look at something like transcendental functions, right? Transcendental functions, when you look at here, the coefficient itself is also actually in a higher degree. So solving the transcendental function, the same approach is same. Yeah, it might look slightly complex that we like here we have the we look at here, we have the degree of power 2. Now we have this coefficient here itself is tangent of power 2. So this is quite interesting actually transcendental functions. Now if you want to block it, it will look something like this. Yeah, quite interestingly looking. Now if you say, hey, could we actually look for global optimum from these particular transcendental functions? Now if you look at here, quite obvious, right? If you look at local optimum, that would be somewhere here. Yeah, either this one or this one. Yeah, graphically looks both of them actually are touching as one the very bottom point of this x-axis. We're not too sure which one actually is the considered global minimum, but let's try to solve it. So now, similarly, I already block it with these particular transcendental functions. Now, the next thing here, I just define my solutions. The solution is very straightforward. Now, I only have to define my functions, tangents, for x squared plus x squared minus x, and only have to tell the range between -8 to 8, where x in between here. Now I'm going to ask the system for the range while x is from -8 to 8. What will be my current actually minimum value? So I say put minimize. Now this entire actually search of the this optimum might take a little bit computation time. It might take about 20 seconds, so let the system do a computation. Oh, no, it came out earlier than I expected. Now, you see the output here itself. Now, the solution, now in terms of also the solution could be in terms of transcendental function. We see some of the, even sometimes it shows some logarithm output. Yeah, this is something what we expect. This is symbolic output. But we say, okay, I do want to look at this symbolic output. Can you give me actually numeric output instead? So what we have to do is, instead of actually using this symbolic approach, I say I'm going to convert it into a numerically approach where I put n in front. So the whole solution right now will be in a numerical output. So it's quite fairly simple for us to see, especially particularly in the engineering and production. Now, if we have this numerical input output here, we have this x and y. And similarly, you say, okay, now using exactly the same approach, I'm going to append this value of x and y and put a point size of 0.05, be a red color. And now I say going to superimpose these two actually. One is original graphic, there is solution. Now, if it tell me that actually the global minimum value is somewhere here. Yeah. So fairly straightforward, isn't it? So even though the actual equation itself might looks like, especially when I deal with transcendental function, looks like slightly complex, but you see the entire flow is just like as consistent as before. Now, let's further look at one more example in nonlinear equations. I'm going to share with you later on if you want to approach, you will like it a lot. Yeah. Those who are not unfamiliar with Wolfram language, right, you know we have something called Wolfram Alpha. Now, of course, like if those actually hardcore programmers, scientists, and engineers, you might not actually pay attention to much of this. But if you're new to Wolfram language and you're engineers, you are not programmers by training or programmers by your profession, you would definitely love this one. But now, I'll now give you another slightly much more complex transcendental function now with logarithm function inside. Now, and we will see, this is something that you commonly see in textbook, yeah? And we see here we define x is bigger than 0 and also while y is bigger than 0 when x and y belong to this z domain. Now, what we have to do here is, again, no matter how complex it might look mathematically, we just actually say, hey, I block it accordingly in x, y. So we see that this is not 3D display at x, y. Now, if we want to look for, again, an optimum point on this particular transcendental function, slightly more complex than just now one, same approach. Now you see the workflow is like coming up very systematic to you right now. Now I want to do optimizations numerically. Now it's say, hey, I want to again minimize. I say and minimize, numerically solve it. Now if I numerically solve it, again, strictly it can give me an output right away. Say this is z will be 935.68, x is y is y. So again, can I display this solution graphically? I say definitely. I run it. Give me actually this particular optimum point with this constraint domain. Then this will be a global optimum in this constraint domain. Now, if we look at here, the approach here is very simple already. Now, if you say, hey, Peter just now mentions about Wolfram Alpha, what does it have to do with that? Now, let me show you quickly, because of course today we are not here to show you about Wolfram Alpha, but seems I saw some names here are slightly like stranger to me. I believe that maybe you are new to Wolfram. So now I will share with you how this thing will work actually in so-called Wolfram Alpha. So now, if you want to, for instance here, I just copy and paste this whole thing. You don't necessarily have to actually do a very nice syntax like this one. You can actually ask very plain questions. Now, to make things simple, I go back to previous one like this one. Go back previous one like this one. Like for instance, a syntax like this, anyone can write. Yeah, anyone can write. So if I say this particular syntax, yeah, particular syntax. If I in a normal persons, right, for instance, I put a double equal sign. Now, like I say, those who have not come to our training before, you might not seen this before, but those who are regularly actually been using Wolfram Mathematica, you know that Wolfram 10 over years ago, they already come out with something like almost like AI. It's not exactly AI, but it looks like AI. It's something called natural language input, something like ChatGPT. So if we say, hey, could I minimize this thing? I just type in plain English. Now I hit this thing, and the system will actually automatically go through the whole process of the searchings for the optimum point for us. So now the system right now, in using this approach, right, because using natural language input, you need actually connectivity to internet. Now you try to figure out what your instruction is, then you figure out what method to use, and figure out actually what should be a proper syntax. Now you can see here the system realize, in fact, this is something what we try to do. Is say, hey, in fact, you want to actually minimize this function with the domain while x is between -8 and 8. Now, the system going through a series of local minimizations. Now, this is like you do a searching here. Now, this is entire, for instance, here, it say, can I actually find no global optimum? Can you show me step-by-step solutions? What do you mean no global optimum? The system will try to actually show step-by-step solutions. Let me see whether I can expand it. Yeah, it will take some time to show the entire step. Now it's coming up. Yeah, step-by-step solution. So happen this one you can't find it. It's okay. We leave it now. We see the whole output here. You will find actually in from this -8 to 8 here, this compared to what actually we came out and say, hey, this is like entire global optimum is here, but it's searching for all the local optimum for all the particulars that turn a curve here. It's interesting enough. Yeah. So in order to give you actually, we want to look for global optimum of this particular actually function. It gives you a local optimum for every turn a curve. Let's say, for instance, here I say, hey, what if I want to look for minimize globally? Let's see what I'll come up with. Yeah. The system recalculating right now. He's saying no global fine, but it's okay. It's okay. But it gives actually quite a good actually a first round of approach. Now, of course, there's some when we have free time, we can try out more. Now, let's further look at this one additional function here. That will be the last example that I will share with you on nonlinear optimizations before we go on something that's very interesting on linear programming in the example for the businesses and industries. Now, this is like some of the very common, actually, typical 101 kind of actually problem I deal with. We have a constraint x squared plus y squared equal to 1. Pretty much is a cylinder, yeah? So if we have an x squared y and we want to put a constraint in the cylinder, how does it look like? Now, again, this is like two plotting. First plotting here, I say, hey, I'm going to have plotting of 3D of this point x squared y. Yeah, I'm going to do a region plot. This will be the cylinder, yeah, display. So how does it look like? Yeah. Now, show visualizations is very important. You say, hey, this particular cylinder actually is a boundary. I want to actually look for a particular actually optimum that is actually constrained in between this particular cylinder. So what will be the optimums that I can find in this constraint? So at least visually right now, I can see it very clearly. Now, the next thing here, if I want to look at actually 2D display, of course, when we switch 2D, we just use contour plot. Now, we put this particular, actually, this 3D display together with this cylinder. So we know that actually the regions of the optimum point we want to search actually is fall inside this particular circle. So we have actually 3D view, also 2D view using contour plot. And again, as I mentioned here, the super function that we are using here is like this show. Simply, we put as many block functions that we want, then we show them actually one go. So it superimpose one another. Now, it's very clear right now. Now, we want to actually, of course, you say traditionally, how do you solve this thing? Now, we use a Lagrange multiplier and some partial differentiation, but today we put aside all those actually methods. We just say, hey, use of building automated methods, look at my function, look at the natures of my polynomial, decide a method to use. So system, in fact, is doing a serious automated search of method for me. So I say, okay, do a minimize. Now, the system find it, now minimize. Numerically, give me this answer. If I say, hey, I want actually exact solution symbolically, so I just turn away this n, so it give me the actually symbolic solution. Now, if I put it n back again, now this example I think is easier to use Wolfram Alpha. Let me try again. Now, again here, if I have this thing, I just copy this whole thing. I just say, hey, help me to do it automatically. Yeah. I just say, figure out what I'm trying to do. Then help me to come up with certain solutions common user might have. This one works out fairly well. Okay. Function x squared 1, and my domain is x squared plus 2 squared equal 1. This is my constraint. Say there's a unit circle. Now, for x and y. Now, quickly give me actually this particular plotting. It plots even better than mine. Yeah, it's better, but it's clearly than mine. See, this is about the constraint. Like, it give me actually immediately give me two give me two optimal already. A global optimal. This 2 point here. But in our common approach, right, what we will do is like this. Of course, I said at least using this Wolfram Alpha, it give me actually some of those actually display I common people might try and look at. Now I say display solution graphically. This is what we will do using previous approach of workflow. This is my points. Append value of x and y. Show the block. Now I say show the block. Now system showed it here. This is my way. Yeah, this is one of the global optimal finder here. Yeah, this looks quite, yeah, it's identical result. Only thing is that the way display style different. You will see the previous display here using Wolfram Alpha actually nicer than mine. Yeah, nicer than mine. Of course, you say how to extract this output. You can always extract the output from anywhere on the system, be it your own functions or the output by Wolfram Alpha. It doesn't matter. So for instance, I just copy, I say, I prefer this output to show to my student. Can I just paste here? Yes, you can. You just paste here. And this is, if you ask the system to display the equation or the code for you, how this display nicely come out like that, how do we do that? Yes, of course, you can ask system to display the code for it. But now I just want to display as an object so I can actually demonstrate in my class. It just looks like that. The last thing here, I say, hey, show me the control block. Now, it gives me one of the global optimum here. Yeah. Now, this is something what we generally do for engineer approach and numerical approach. But when it comes to how we do this particular actually convex function, convex constraint. Now, this is like more linear programming. Yeah. And this is, sorry, the title here put non-linear is wrong. Okay. I give you one. This is one very interesting example when it comes to business world. Now, we know in Malaysia government last year, Malaysian government is quite ambitious. Government actually already hit a target. In most of populated city in Malaysia, we have 90% 5G coverage. So we look at entire internet speed, we are quite good in the world ranking right now. So we can compare like 5 years ago when people complain, oh, we have actually very low internet connectivity speed compared to Korea, country like that, or Singapore. But now we are quite, unless some of the very rural area, we are quite better off right now. But the thing is, a 5G deployment do not come cheap. And also there's power consumptions. We want to solve issues like that. Now, if you say, hey, Peter, we talk about convex functions, right? What are functions available? There are many functions available here. As I promise you, I will disclose to you where are the built-in tutorial or documentation or the complete guide. What methods are available there? Yeah. For instance, like SG splitting conic, CSDP, semi-definite, DSDP, semi-definite. Some are familiar to you, some maybe unfamiliar to you. There are many methods. Now, how do I know which method to use? Like say it's automated, but you say, hey, Peter, I don't want automated. How? If I want to actually compare with the result, let me show you. Let me go back to a previous example here. Now, before I move on to some of these business solutions. Now, for instance here, I come to here. I'm doing this numerical estimation. Say, what if today I don't like this approach? Can I actually define certain method that I choose to use? Yes, you can. For instance, here, right? If I put in here syntax, let me make it bigger. I put a 1 comma size here, comma size. I say, I put in, let me make slide here. Yeah, okay. I just type method. Now, if I type method here, the system asks, what do you want? For instance, these are the methods available. I can choose from differentiate evolutions, random search, simulated net links, netted meat. So for instance, I say random search. I want to compare random search. Again, if you say, okay, this method you use random search, let's try to use this method. Now, there's no change result. Now, if you say, hey, how about a post process? Could I use interior point instead? Now, there are some other things you can put in here. Yeah. For instance, here, if I want to put slightly more options, say, hey, okay, the method is random search. Now, I'm going to have one more thing to be like further specific. I want to be like post process. Now, post process. Okay. I want to have it like, okay. I say, give me interior. I hope I spelled correctly. Now, because I'm just typing right now without using any method, I might actually wrongly type something. Let me try again. Let me try one more time. Post process. See. Okay. The method, there shouldn't have parentheses here. That's why it did not come up correctly. Method, random search, post process, interior point. Here we go. Now you can specify what method you want to use and the post process that you feel that you want to use it. And every time if you want to use some of the like things that the built in accordingly, you can actually follow some of the steps that you want. And for instance, here I say, give me automated one. I don't want to actually specify the interior point. I say choose it for me. Yeah, the system it choose for me. Say change to automatic instead of true. Say I should change to automatic. Let me see, automatic. Yeah, here we go. Yeah. Now, so you could see here, I can actually go to be a very many manual manipulation if I want to. But now, since we have almost come up with time, we have about 45 minutes. So I quickly go through these interesting business solutions. Yeah. Now, for instance, here, when it comes to this 5G transmission tower, right, I have several constraints you need to consider with. I give one quick example here. For instance, I have actually this particular SY coordinate represent these GPS coordinations. Yeah. So I have like a 10 taman. Yeah. I put in paper. This 10 taman have different GPS coordinate. Now, if I put the center of the taman here represented by this point, XY coordinate GPS, right? I say I only have budget for 3G tower. N power towers 3. Yeah, this is total budget we have. So only the next thing here is how could we actually optimize the coverage of this 5G signal to all these 10 taman at the same time want to minimize the power, because I do not want to have certain actually transmission tower to have need to boost with so much power, right, in order to cover too many number of tamans. The area coverage of 5G also have limitation. Of course, number of the devices it can connect is hundreds times better than 4G. But again, in this particular example here, I have 10 taman covers, and I want to make sure my power consumption is not something above my quota. Yeah, I have my budget on number of tower, but I do not want to have a power consumption monthly more than I should. So now, this is my constraint here. Now, the objective, we try and define objective here. Now, do not mind about some of the syntax here. Those actually mathematical syntax pretty much by how you do it textbook. Yeah. So we just convert this textbook to a slightly in a coding approach in Wolfram language, but trust me, the coding approach here is much, much simpler like what you do that Python. Yeah. Yeah. So for instance here, the functions given here for each 5G transmission tower consume power proportional to the range, which is given by R with a power with exponent 1.5, yeah, power to 1.5. Now, with this, so we're going to have a summations. My objective function here is summations of 3 power stations. Now, if we expand it out, this is how it looks like. Yeah, 3 power stations, 1, 2, 3. Yeah, with the exponent 1.5, 1.5, 1.5 each. This is our objective. We want to actually minimize the power consumptions. We want to minimize it. This is our objective, and this is our constraint. Now, the next thing here, we further define our constraint now in more detailed manner. Now, the decision constraint here, first thing, the few things we're going to consider. Now, it's become very real life already. Now, it might look slightly messy on screen, but trust me, this is what you do on paper as engineer or mathematicians. Now, first distinction constraint here is we say, hey, our communities that need to be at least covered by one transmission tower. I know in my community, of course, if you say for safety consumption, if you want to have backup and sensitive, if I have a sensitive actually application like hospital, police station, I want to make sure they're at least covered by two 5G transmission. You can put it here like here. At least I want to be like 2 to 1. If you want 2 to 1. But here I stay as the normal residential use. Each of the diamond covered by one transmission tower. Fine. Now, after that, I say this is each cell tower must be located such that its range covers some of the community. So I have a distance actually constraint here. Distance constraint is something like we define. I will not explain very details here because the syntax here, if you want to look here, go through my one here, no point. But just let you know here, this is defined how the range must at least cover like the maximum you can cover up to like this m with a distance m, but you need to cover some of the communities here. We say, hey, let me see, m is 20. Yes, our community we have 10, m20. I think it's 20 kilometer, if I'm not mistaken. These original questions. Never mind. The next thing here, this is to define the number of the community it can cover. So the system can say, hey, that it doesn't mind if some of the community get overlap. We not purposely say that each community must have more than 2 towers, but the system say, I want to minimize the cost. Each of the community will at least cover by 1 tower, but each tower can cover more than actually several communities. And each cell tower have minimum maximums of coverage. This is how we define here. So we have minimum how many it can cover multiple communities, and also it can actually minimum maximum coverage. So we put all the constraints, 4 constraints we define in details. So this is like detailed constraint. Looks like I agree, but it works out fine. It works out fine. So lastly here, this is our actual workflow. We say we want to optimize the cell power position as range. Now, again here, the objective super function we're going to use here, as mentioned here, this is a convex function. We have convex actually constraint. So we use this approach called convex optimization. These are my objective functions. This is my decision constraint, distance constraint, coverage constraint, maximum coverage constraint, and with my variables. So it's put things according to the syntax it asked me to put. Yeah. So that's all. We are done. We are done. So there's some warning here. That means run this part, the variables. Make sure I define variables properly. Now, this should give a result right away. It will take several actually seconds to do the computation, search for the optimums, let it run. Now, you could see this entire approach here, right? Again, we are turning into a workflow. Either with these convex optimizations, or later on we have said convex optimization, linear, fractional linear optimizations. We're all going to use actually same approach. Yeah. You can see here, last 2 approach here, we want to visualize position and range on tower. We respect the community location. Now, let this run the computation first. If some of you have questions, let me see. There are some questions coming on chat room. Let me see. I can take a chance to answer it. No question now. Okay, fine. If you have a question, you can put in chat room while we are waiting for the output to come out. So almost there. The last time I ran it, it took me approximately about less than 1 minute. Yeah. Let me see. I switch off some of the browser background. See, it could be like faster. Okay, done. Fantastic. So now The problem was solved, but the gap between conic subproblem and linear subproblem was greater than the tolerance of 1 over 10,000 with the best result found. Okay, good, good, good. Seem to be you found the result. Now, this is like the immediate actual result come out with the XY coordinate where we actually erect our 5G transmission. I say fine, okay. Then in this case here, can I actually turn this thing into something that more easy to understand? So it showed me that, okay, this is where it's erected and the tau range that the range that the powers used to boost, this is covered at radius 0.25 kilometers, covers 0.79 kilometers. This covers less than 0.04. This is like a bit unpractical, but doesn't matter. This is solution it come out. Let's visualize result. Yeah. So I put together with all the 10 communities with the transmission tower. Oh, it looks fine. See, this is first of the transmission tower. It actually with higher power consumption, but area it cover nearly about 7 communities. While the second one, it only covered 2 communities and 1 of communities of age. Again, because this is whole thing is using the optimization, even if for the age here, it considered fulfill because it's just right and fulfill the constraint. But of course, when it comes to commercial application, sometimes you need to put in some safety percentage. But in this case, we quite likely going to boost a little bit more the power to make sure that the signal received in the last community, the age of constraint here is considered reasonable. Another thing here is this one is, it seems like based on current constraint, this particular signal seems only can serve this little kampong here by itself. So of course, we do not put in a constraint of the total amount of money need to put up to erect the transmission tower. If you actually put that one is constrained, quite likely this thing shouldn't exist in the first point. But of course, mathematically, it does satisfy our optimization of power consumption, but of course, without considering about the total cost on the infrastructures, things like that might come up. So the next thing is we're going to look at some of the stations with a more actual broader consideration. Now, this, again, for a quick overview here, like how we actually do optimizations on linear programming, these parts here, we use a lot of convex linear optimizations. Right-hand side here, we have 3 super functions: minimize, numerically minimize, fine minimize, and fine fit. Today, we will not talk about fine fit, so I only share with you so far shown on minimizations, numerically minimization, also fine minimum. And this part here, as I promised, I will disclose to you how we can do this thing on your own. Yeah, it's very simple. Now, let me further move on here in the last 20 minutes, how we can do actually furthermore like convex optimization on this linear programming. Now, for instance here, unfortunately now war is much more complex in a lot of conflict and warfare. Those things is not something we want to purposely play with this calculation, but in the real world, there's many things that is no choice part of cruel reality. But we know that linear programming came out actually quite early in the 20th centuries, but only it became more popular when it comes to Second World War. And scientists realized that linear programming can solve a lot of logistics and also strategic this military deployment. So we use this one, the classical textbook 101, to see how we can use this convex actually optimizations in linear programming to solve some real world issue. For instance, here we have 5 military installments, yeah, and there are 3 base camps. And these 5 military installments could be like in forests, in sea, soil, in cities. And the problem here is during a time of emergency when these 5 military installments face attack, the authority in charge need to dispatch actually soldiers from the nearby 3 base camps. So now the question here is to ferry those soldiers from these 3 base camps to these 5 particular installments come with different costs. The cost I think very straightforward is logistic cost. Second thing could be the risk involved. How much risk is or the distance. So the total cost could be like in as a functions for the uh, uh, in terms of total distance travel, in terms of the risk involved, in terms of the facility needed to get the soldiers come from one place to another. But let's put that aside, we just convert it dollar and cents. For instance, here, if I go and dispatch, right, soldier from this particular base camp number one to these five respective location, each locate it will cost differently to them. For first soldier camp, right, to send to location of one is like, for instance, you need a camp, the cost. Send to second installment, the second location, will come in a cost unit of 15, 10, 20. Similarly to second army base, right, it will come with a cost of 15, 10, 10, 15, 15, and third army base with 10, 25, 10, 10. Now, if we're going to put this thing in a bar chart to visualize in the Excel spreadsheet now, since we're talking about bar chart, the visualization in Wolfram is very, very powerful and very colorful and very exotic. Whatever you can do with Excel, whatever you can do with business intelligence application, Wolfram can do the same, if not better. And can even do it programmatically. Now, this is the best part. You can do it programmatically. That means whole display is dynamic. Now, we could see here, these three army camp, when dispatching soldiers to five different locations, will have different costs. Yeah, B1, B2, B3, B4, B5. Yeah, B1, B2, B3, three particularly these locations. No, I should change to not B. Yeah, to be military installations, M1, M2, M3, M4, M5. Let me change the legends. Now the legend changed. Now, after that, we need to start defining our objective. Our objective is very simple. This is my total cost. Yeah. So I say in this total cost, then the five different installment or the location I need to send to. This is in the matrix. Yeah, in a form matrix. I say I want to get it for second column. It doesn't matter. I just want to sum up the total cost for the product between the cost of dispatching the soldiers and the matrix of this particular five installment. So it looks like that. Yeah, these are product of the cost and the locations. So this number two is, I say I want to only show column number two. Yeah, say why column number two. Don't mind about that. In this particular case, this is how we want to display it. Now, I hide it fine. My objective is fine. The next thing very simple already. This is my constraint. The constraint only have two. Maximum soldier, for instance, here, right? I can send out for each particular particular camp, right? Each camp can maximum send out 100 soldiers. I only have 100 soldiers from each camp. That means totally I'm 300 soldiers. But each camp, I only can afford sending out 100 maximum. And by each of the installation here, right, from the file installation here, each installations, right, I need to have at least like 50 soldiers to come to help guard the area. That means I have 5. Yeah. So if each of the installment, I have 50 soldiers, totally I need only 250 lah. But I know I have 300 soldiers hands. But minimally, and each installment I need 50. Yeah, minimum. Yeah, this is minimum requirement. So in this case here, we can perform linear convex optimization very easily. Now, again here, I do not have to clap my hand. I only have to ask the system, okay, this is linear optimizations. Yeah. My objective here, super function is called linear optimizations. Now, I have these two constraints. Constraint here, I just put in this curly bracket, say maximum soldier is my, this is how many soldier I can dispatch. Yeah, this is the first constraint. Second constraint is a minimum soldier I need for each installment. Yeah, I put these two constraints. And R belong to matrices with dimensions, my cost. This is my cost functions. I say follow dimension, my cost function. That's it. This is a common way to define our linear programming. Yes, very common. So if I say how this looks like, it looks like this. Very simple. Yeah, these are very common linear equations. Linear programming. Yeah, very common. So now, when the system know you need to do a linear optimizations, right? On that, we say, let's visualize a result. Yeah, I just put the result here. Just now the result already came up. So the result just now come out is I have 50 from Social Camp number 1 sent to installment number 1, 50 soldiers sent to installment number 4, and 50 soldiers from Army Camp number 2 sent to installment number 2. 50 soldiers from Army Camp number 3 sent to installment number 3 and installment number 5, respectively. If I want to visualize result, you see the approach is same. How do you say visualize it? I can visualize it in the graphic form, like the 5G transmission tower, or can visualize in a table form. So it's quite easy to see. Now, from this base camp number 1, I send the installment 1, 2, 3, 4, 5. This is how I can distribute it. So Army Camp number 1 to send out 100 soldiers, 50 for settlement 1, and 50 for settlement 4. And second Army Camp only send out 50. And third Army Camp send out 50 here, 50 here. So done. So you can see, using this approach now, we say, oh, Peter, this is quite simple when it comes to the enable programming 101. Now we come to something much more interesting. How about fractional? Now, in the real world, right, a lot of the optimization are conflicting one another. If you're maximizing something, at the same time, you want maximizing some other things. So in this case, if you deal with the same situation here, right, you say, hey, I want to maximize, yeah, for instance here, I want to minimize the cost transportation, but what if? How about the survival odds? Survival odds is something you want to maximize. When you're sending soldiers to nearby actually a battlefield, it doesn't mean that each of the base camp soldiers have same skill or same equipment. You're sending actually Marine to somewhere, for instance, not Marine, who are sailors, who are you're sending them somewhere to inland city battlefield. Definitely, they're not going to do well. Yeah, you send Marine there, it's not going to do well. You're sending actually foot soldiers actually fight actually the war with somewhere near seaside or somewhere near actually riverside might not do best to their expertise. So we want to minimize the costs at the same time want to maximize our survival odd or our actually winning odd. So these are two contradicting constraints. So this is considered fractional. So in this case, what do we do with that? So first thing here, this is my cost, like previous one. This is my cost. If I put in my cost here like this, there's no change. Yeah, its cost is like this. Let me just change this thing to M1, 2, 3. Put the L is easier to understand. Location 1, location 2, L2, L1, L2, L3, L4. So this is like cost incur. Similarly, if I'm going to send out all the soldiers to different places, they also have different survival odds. So same thing, I put in L1, L2, L3, L4, L5. So this is how it looks like. So it, obviously, like Army Camp number 2, right? They are their skill is much more like in average in different type of combat environments, except in actually location number 5, they are not that good. But Army Camp number 1, right, they are very good in location number 5. So their survival odd is up to like 20. And Army Camp number 3 seems like quite well trained. They are generally actually higher than Army Camp number 1 and 2. It's like as much as with the unit of measurement is 20 across all location 1 and location 4, except for location number 5, they have 10. Yeah, they are actually the same as not the same. They actually lower than the rest actually of the Army camp in terms of their equipment and maybe of their skills or when kind of better experience. Now, since we already have these things, right? The constraint, we already know these situations. Now, we start defining our objective. Now, our objective, like I mentioned here, this is a fractional objective. Maybe our objective number 1, yeah, it's total cost. Now, objective number 2 is a survival odd or the better power. So we say we define objective 1 and 2. Both of them are actually conflicting. Now we put our constraint here. Our constraint are same thing as previously. Yeah. Now we can send out maximally 100 soldiers from each army camp, and each of the battlefield location 1 and 2 and 3 and 4 and 5, they need at least 50 soldiers to be there, yeah, to help them as backup. Now, we're going to perform something called linear fractional optimization. Previously, we have a super function called linear optimization. Now, we only have changed something called fractional, linear fractional. This is not super function. Now, we put objective 1 and 2, yeah? 1 divided by 2, because both of them actually are conflicting. Same thing, you see the constraint the same. Max soldier, minimum soldier, and they're also subject to the matrices dimension follow my cost. If I put like this, the system give me the solution right away. Now I say, okay, let me visualize the result. I don't want to look at this output in the list, but I want to give outputs in the table. Quickly, you see this output here. This looks quite different from previous actually output. Previous output, without considering the survival odd or combat power, you simply look at how to minimize the total logistic cost. The result is quite different. So now, this is quite interesting. And last two examples here also very interesting, getting more and more actually complex. Now, for linear programming here, in a real world, we need to deal with a lot of things. They are not definite. They are involve many uncertainties. Now, if you're dealing in the manufacturing world, right, I mean, this field for nearly 20 over years, a lot of things are quite easy to solve. But when it comes to mathematics, try to solve this thing together in programming, right, it's not simple because it involves a lot of fluctuations and variations. The things actually come with a lot of uncertainties, a lot of things not able to optimize that well because uncertainties, yeah, fluctuations. Because when it comes to real world, there are human errors, there are waste, there's unexpected events, there are randomness involved, either from defect, overproductions, fluctuations like the unnecessary waiting time, and some people who are mismatched talent, and also there's some transportation issue, and there's some extra unnecessary step processing. And human, not machines. Yeah, that's why we try to make things robotic in when it comes to Industrial 4.0 to make things like more predictable. When things are more predictable, you can do a lot of prevention. You can cut down all waste. But in real world, when you need to give it uncertainty like this, no matter how robotic it is, there always bound to be some uncertainty. For instance, here, the normal actually station is quite straightforward. How do we actually maximize my profit? Maximizing my profits involves several things. In this case here, I make it very simple. We have 3 products. Each of them actually can sell this much, 90 ringgit, 100 ringgit, and 70 ringgit for product 1, 2, 3. Yeah, very typical linear programming. I also have costs. Yeah, the cost 45 ringgit to make product A, 40 ringgit to make product B, and 20 ringgit to make product C. And also, in ideal situations, right, if you fully run the factory for product A, right, you can get 100 units, yeah, either per hour or per day, yeah, doesn't matter, or per shift. And if you run it actually full force only on product B, you can get only 40 units over a certain period of time, and you get 60 units over a certain period of time. Now, the question here is, how do we actually come up with good combinations of these 3 different products so I can have a maximum profit? Yeah. So now, if we put this thing together, the thing is very simple. Now, this is how it looks like. Machine 1, 2, 3, 4, you will see here, each machine has different actually machining time. Yeah. Now, if we say, I already know if I run certain product full force, whole factories, I can get this X output and that output. But each machine also has different, we have 24 hours or maybe 8 hours per shift. Each product running through each machine have different time involved. So the question here, could we have combinations of products? Not just actually maximizing my profit. I want to make sure that I subject to constraint on the machines that are available to actually to load on those products. But make things worse. Actually, like I say, in real world, right, they deal with a lot of uncertainties. This is reality. For instance, here, this is like market fluctuations. No matter how good you make your forecast is with machine learning or with some traditional forecasting method, ANOVA method, not ANOVA, some of the methods that you have, like no matter what algorithm you have, we're not going to have absolute predictions, right? So this is like the frustration they have to deal with. For instance, here, the revenue, they have maybe frustrated by 5 ringgit. Yeah. Because market fluctuations, each unit of product may decrease by 5 ringgit. That means that over the time that they could decrease 1 ringgit, 2 ringgit, 3 ringgit, 4 ringgit. Particularly now it's true because Malaysian ringgit depreciations. So let's say we put that thing in, the total revenue can actually, in the ideal time, I'm not going to lose anything. When price 10 ringgit, I get 10 ringgit. But some worst time, when price 10 ringgit, I get back, might not get 10 ringgit, I get 9 ringgit because of fluctuation of ringgit. The total actually value I get is 9 ringgit. Yeah, that could happen. Same thing here, because the machine is not perfect, yeah, and also have 5 units. That means that I can put in a percentage if I want to, but I make it simple. Say the manufacturing capacity that could anytime decrease between 0 and 5 units per product, the total actually capacity. Similarly here, I might have actually lost time. This lost time could due to many reasons. Yeah, it's not because the machine actually reducing the capacity, but I have lost time. Maybe the human supposed to man the machine is not there, or material is not there. So I could have lost time as much as 2 hours. Yeah, this is per week. That means that for sometimes, right, when it's actually breakdown, I need to restart again. I need about 2 hours to make it come out again. Yeah, so I could have lost time between 0 to 120 minutes. This again uncertainty, and again another uncertainty is for unknown reason I could have certain wastage, certain waste. So waste again could be like 5 ringgit per unit for unknown waste. So we have 4 different uncertainties. Now, with these slightly more complex situations, right? Now, our objective function is still very simple. Revenue minus cost n times the numbers of this matrix of X, number of products, a mixture of products are going to produce. This is very simple objective functions. But if I put in all these constraints together, right? Machining time, capacity time, and also the uncertainty time, I have several actually parameters I need to put in. Variable parameter constraint here, capacity constraint, time constraint. This is something a fixed one. Yeah. And uncertainty constraint, I have revenue uncertainty, capacity uncertainty, the 4 uncertainty, time uncertainty, and cost uncertainty. So I just put this actually the variable constraint, primary constraint together in these mathematical equations. Same thing, I think, follow textbook. I just follow textbook. I just convert it into this syntax that Wolfram can understand. Now, the next thing here is very super easy. I say I want to use one of the convex optimization. I use robust convex optimization. You say, Peter, why robust? I will not explain here. There are some other convex optimization method you can use. I choose robust. Yeah, I choose robust. Now, this is the profit. I say, if I going to do a worst case scenario, give me the global minimum. Yeah, minus profit. I put minus. What's the worst case can come out? Now, I put in the parameters, uncertainties parameters. Now, I say this follow the space vectors of 3, and it should give me integers because there are 3 products. This is worst case. That means that I have lost time, 120 minutes. I have lost my profit by 5 ringgit because of frustration and productive. 4 different uncertainty, all go for worst case. I will have a product mixture of 77 for product A, 17 for product B, 55 for product C, and this, when worst case scenario happen, I'll run from this combination, you give me the maximum profit. But now, can we turn it into be user-defined functions? Say, okay, now this is the best combination, but I want to turn it into be a function, so I can use it over the time. Now, if I turn the function similarly, I turn to parametric convex optimization. Let's change this thing called to parametrics. Convex optimization, I can turn into function. So next thing here, I say, okay, give me a best case scenario. Best case scenario, that means that all the four uncertainty all turn to zero. That means that there's no uncertainty at all. The four uncertain, no uncertainty at all. That means all zero. Best case scenario. In a best case scenario, I can have total this profit 7,650 if I follow the output 821660. Yeah. Similarly, I want to make sure I do it correctly previously for worst case scenario. I plug in the previous actually output. I say, if I have this 223, 155, all the lost time of 2 hours, yeah. Also, I lost 5 ringgit for all the uncertainty, all the worst case. I say, in that case, what will be the combinations? So the combination will be 77, 17, 55. So you go back, it's the same here. It's a worst case scenario. And the minimum profit I'll get in worst time is 6,137. So during best time, I will earn additional about 1,500. Worst case, when all the things not supposed to happen together, I will actually have lesser about 1,500 about that. Yeah. So now, today I'll close it here with a simple actually example. But I say, hey, Peter, how about this method actually? I want to know what's the method available. Inside Wolfram language, if we go for documentation, you type up cost optimizations, right? It will give you all the details, documentation, and example, how we deal with global optimizations, local optimizations, how we solve the optimization problems, step by step, example, tutorial. For instance here, if I want to solve numericals, nonlinear local optimizations, I want to find out what will be, for instance here, if I say, let me see, algorithm, yeah, this algorithm for linear optimization, and look at algorithm. What are the algorithms make use of? If I further scroll down, let me see. The algorithm. This is application. You see here, there are application of engineering, application design, or optimal trust. Let me see where the algorithms are. Ah, linear optimization functions, methods. See, that's method uses. Here. The method options specify algorithm used to solve the linear optimization problem. Problems, values, automatic, simplex. Yeah. You write simplex, interior point, CLB, MOSFET, and GLOBE. The default is automatic. If you say, I do not want to specify anything, the system automatically search the best. It consider the best, most suitable actually method to use for this optimization. If you say, hey, I want to choose interior, yeah, or want to choose a simplified simplex, you can actually specify using that approach I showed just now, just choose the method accordingly. So the rest actually, the guide is very, very complete already. So you just look up any one of the actually topics that feel interested. And also inside Wolfram website, there are several other actually already ready-made videos that talk about optimizations for engineering. And if those interested, particularly related engineering questions, they actually can look at the video available. Hopefully today with this 1.5 hours, I'll give you a quick overview how we actually can get started with this optimization for linear and non-linear equations. So let me see, are there any questions? Okay. If there's any questions, I'll stay on for 5 more minutes. You can ask any times. So if not, I'll ask Desmond to put up the link for certification. You can get your digital certifications. Yeah. And again, that you can always try to text us and also contact us. I'll put in my email address in the chat room. If you somehow say, I need to ask you some questions related to your own project, and you can actually email or contact me directly. I'll try my best to give you some guide to my capacity. And also another things we offer to Unity Malaya community is, I know not all of you actually might be in the fields of optimization. You could be coming from different fields. And we say, Peter, how about, for instance, over the time, a lot of people ask about questions about data analytics. Is one of the very hot topics and out there in market. Say, could you show us more about data analytics in this particular area's application or that area application? Could we have a short webinars or hands-on workshop? Do contact us. We will collect all those opinions and requests over the time. At least every quarters or every 2-3 months, we will work through with ICT departments or Unity Malaya. So with the permission, then we will actually organize either webinars like that, or occasionally we might come to do an on-site workshop if necessary. The last on-site actually a workshop we had is, I think, we Faculty of Science. That was like about 6 months ago. So again, if anyone you are willing to have a workshop on site, and you can always talk with us, and you're willing to do some arrangement on that, we are happy to do it. And all those things are free of charge as part of our friendly collaboration with University of Malaya. Yeah. If not, we thank you very much for attention and also attendance today. So I'll play a little video once more time, and then after that, I'll come back and stay on 5 more minutes. If you have any questions, then you can actually try raise again by then. And yeah, thanks very much. Okay, and